All right, so lesson 4 here, we're going to take a look at data sets of two variables, looking at how we can display data, and then lines of best fit, talk a little bit about correlation, and then residuals. In here, the chapter kind of shows some things that have to do with the calculator. We're not going to look at those so much. We did do a lot of work with the calculator with the stats tables, but for this specific chapter, it doesn't really give us the data necessary to use the calculator, so we're not going to take a look at that until lesson 5 when we look a little bit more at best fit lines. But to start off here, we start off with, it says, linear equations are often used to model real-life relationships that involve numerical data in two variables. However, real-life data does not always fall neatly along a well-defined line. So we're taking a look at scatter plots. A scatter plot displays data corresponding to two variables at once. To create a scatter plot from a data set with points x and y, plot each point individually on a coordinate plane. The points on the scatter plot may appear scattered or may appear to follow a path. So again, a scatter plot is just plotting data sets using x and y coordinates, right? And if we take a look here, they give us 3 or 5 different examples of scatter plots, and they talk about correlation. So correlation is a measure of how strongly two variables are related. So if we have a positive correlation, that means the variables increase together. So if we take a look at these two positive correlations, as our x's increase, right, the y's also increase, creating a line or creating a pattern that looks like it could be represented by a straight line with a positive slope. If there's a low positive correlation, again, everything's still increasing, right? So as we go from left to right, we're going up this graph here. But if you take a look here, if we were to draw a line, the points aren't as close to this line as they were for the high positive correlation. So they still look like they're generally going in that pattern, but not as many are going as closely to that best fit line there. When we take a look at no correlation, right? There is no line that we could draw through here that would represent this data, that would help us out here. So no correlation, right, means that they do not go together. No correlation, no pattern. Now taking a look at the negative correlation. So a negative correlation exists when one variable decreases as the other increases. So here, as our x's, right, in this case here, if we're looking at low, start with the high negative correlation. As the x's get bigger, so as we go from left to right, we're actually going down on our y-axis. So here we create a line that's going down and to the right, right? This also would have a negative slope. So when we think of negative correlation, we can also think of negative slope. Just like with positive correlation, we could think of positive slope. When we look at a low negative correlation, again, that still means that as we go to the right, our points are going down, but again, they're not as close to that line as they are with the high negative correlation, right? So they don't go as close together from left to right. So now if we take a look here, it says high correlation should not be confused with cause and effect relationship. A high correlation between two variables does not necessarily mean that one variable causes the other to occur. So just because there's a high correlation doesn't mean that it is bound to happen, but it can mean that there's a possible relationship here. So here it says that Doreen surveyed 10 commuters about the distance in miles they travel to work and the amount of time in minutes it takes them to get to work. She summarized her data using ordered pairs, where x represents the distance traveled and y represents the commuting time shown below. So we have these points here. All right, so these are x's and our y's, x's and y's, x being the distance. X's and y's, x being the distance that she traveled and y being the amount of time. All right, so these are the 10 commuters. This is the distance, this is the time. If we take a look, it would make sense that as distance increased, it took more time. So when we put these on a scatter plot, which they show on page 127, you could see that that is true. So 127, you see our points here. So we have all these points here. And if we were to make a general observation, we would say that as distance increased, right, time also increased, creating what looks like here a positive slope. So this would be a positive correlation. And it looks pretty high. It looks like a high correlation, but to calculate a high correlation, we would want to use our calculator to find an exact correlation coefficient. So here, question 2 says, using the scatter plot based on the data plot, what is the correlation between the distance traveled to work and the time it takes to get to work? And again, here, we'd say it's positive. If you look as the x's get bigger, so from 2, 4, 6, 8, the y's also get bigger for these points, creates a positive slope of a line, so a positive correlation. Next one here says lines of best fit. So when we're talking about line of best fit, we're talking about actually calculating this line that goes through your scatter plot to help model the data set. So it says, in these sample questions, each point represents the distance in miles a commuter lives from work and the time in minutes that person spends commuting. For example, the point at 6:16 represents a person who lives 6 miles from work and takes 16 minutes to commute there. Although the data do not form a straight line, you can imagine a trend line sloping upward and to the right that comes fairly close to each data point. This is an approximate line of best fit. So a line of best fit goes through some of the points on a scatter plot, but it does not hit them all. So the distance between the line and all the points, it is the same as the distance between the line and all the points below it. So when we look above the line, there should be just the same amount of points above the line as below the line, or the same amount of distance. The line does not have to pass through actual points. So if you look at this line here, while getting close to many of the points, it doesn't actually hit any of the points. But if you look here, it has 1, 2, 3, 4, 5 points above and 1, 2, 3, 4, 5 points below the line of best fit. So if we're to look on the next page, it says, a set of data points is shown below. So here we have a set of points. So we have a little bit of a scatter here, but it does look like it's going down in a negative correlation, right? So as we go to the right, as x gets bigger, the y is getting smaller. Then it says, which graph shows a line that best fits this data? So if we're looking for the one that best fits the data, we're looking for the one that can be drawn that goes closest to the most points. If you look at line A, while going through 3 of the points, has 3 points above it without having any points below it. So we want the distance from each point is away from that line to be equal, the amount of distance above the line and below the line. Here, that's not the case. If we take a look at part C here, choice C. If we look here, it seems like while it goes through these 2 points and there's 2 above it and 2 below it, the 2 that are above the line are really close while the 2 that are below are pretty far away. So we'd say that these distances are not equal. D, again, doesn't really go with the slope of this line here, right? This should have a negative correlation, and while it has 3 points above and 2 points below, I don't think we have an equal distance here from that line, which leaves us with B. B does look like it goes through in a general negative slope here, but then also if we take a look, the points look like they have a similar distance away from that line, and there's a similar amount of points below and above that line, so choice B is correct. Now we're taking a look at finding the equation of a line of best fit. So to find the equation, right, there's one way is that we can use our calculator when we're given a data set, and when we're given those points, we'll type them into the calculator. I believe that's in lesson 5, where we'll use more of the calculator. But here what we're going to do is estimate it by using the slope formula and going through and just writing the equation of a line. So it says a line sketched to the points of a scatter plot is a trend line, an approximate line of best fit. To find the equation of a line of best fit, you can enter the points from the graph into a graphing calculator and output a regression line. So that's doing linear regression. as a line of best fit is sometimes known. So these are the steps to use the calculator in the TI-84 Plus. Our steps are a little different, but again, because they didn't give us all of the set points of data, we're not going to do it that way. So if we go over to page 129, we'll take a look at how they want you to do it in this lesson here. So here, we're going to start just down here where it says you can identify. So you can also identify the equation for an approximate line of best fit manually by using any 2 points on the line. So in the example at the right, we have the points here, which is this point here, 1 and 45, and then this point up here, 4.5 and 75. So these are on the trend line. So if we wanted to find the equation for this line here, right, we can start by using the slope formula. So the slope formula is y2 minus y1 over x2 minus x1. Remember, we need to find the slope formula because we need to be able to write the equation of a line in slope-intercept form. And in order to find the equation of a line, we need a slope and a y-intercept. So we start by finding the slope. So we plug in here 75, which is y2, minus 45, which is y1, divided by 4.5, which is x2, minus x1, which is 1. This gives us 30 over 3.5, which when we figure it out is about 8.6. So here we find the slope of the equation of the line to be 8.6. So then to find the y-intercept, we start with y equals mx plus b. We choose 1 point, so we probably pick the point 145 like they did here because they're both whole numbers. And then we can also substitute in m, which we said was 8.6. So we substitute in 45. So we have x and y. Substitute 45 in for y, 1 in for x. Work this out, find that b equals 36.4. So now we have our m, we have our b. We write our equation of our line, y equals the m, 8.6x, plus our y-intercept b, 36.4. And that would be the equation of best fit using the line that they gave us there. So if we take a look at this one here, it says the scatter plot shows the relationship between the average temperature at a sports stadium and bottled water sales. Which equation fits this line of best fit? So again, go through picking 2 points if we can. Let's start with this point here is pretty good. So that point there looks like it is 65 and 6. And then if we were to pick another point on this line at the very top, it goes through 110. So if we use these 2 points, we can find our line of best fit. So we start with our slope. So if we're going through here and we find slope, m equals y2, which is going to be 10, minus y1, which is 6, over x2, 100, minus 65. So we bring this down. The slope is going to be 4 over 35. And if we go through here, 4 over 35, I will find that m is equal to about 0.11. So right away we can eliminate choice C and choice D. So now if we go through, we found the slope, we need to find the y-intercept. So I'm going to choose the point 110 to use because 110 are easier numbers when it comes to multiplication here. And we're going to write the equation y equals mx plus b. Then we'll substitute in our values there. So 10 equals 0.11 times our x, which is 100, plus b. If I go through, I'll get 10 is equal to 0.11 times 100 is 11, plus b. Subtract 11 from both sides, and we'll find that -1 is equal to b. So if I was to write my equation, I'd have y equals 0.11x. Then if -1 is b is -1. When I look at which of these equations is closest, if we look at choice A, it's negative 1.15, which is closer to negative 1 than 1.15 is, so we're going to choose choice A there. So if we take a look at how they did it, right, very similar, except for they chose a different point than we chose, but they still got one that's close to the one we were looking at. If we take a look here, it says that a linear regression model is not always appropriate for data. Sometimes a nonlinear model, such as a quadratic or exponential regression, would be more appropriate. So if we look here, looking at this data set, right, it doesn't show, and there's no one line that we could draw that would be best representative of this data, but this data does look like it could be represented by a quadratic. And similarly, this one does look like it could be represented by an exponential function, but not so much a linear function here. Now, the last thing in this chapter, before we get into the practice questions, are looking at residuals. So residuals from a regression line are used to assess the appropriateness of a linear model. A residual is the difference between the actual y value and the predicted y value from the line of best fit. Each data point has exactly one residual. When using a calculator to determine a linear regression line, the calculator also stores in its memory a list called the residuals. This can be used in constructing a residual plot. So a residual plot is a graph that compares the residuals along the vertical axis with the independent variable along the horizontal axis. So again, we're not going to take a look at creating a residual plot with our calculator in this lesson, but it is something we have done in class. But we are going to take a look at what residual plots can look like here. So if we look at number 5 here, it says, which of these residual plots supports a linear model as a good fit for the data? So when we have residual plots, if it is a good fit, that means that there are going to be points above the axis and below. Because remember, this is how far they are away from the line of best fit. So if we drew a line of best fit here, all of these actual values are above the line of best fit, so this would not be a good fit. If we look here at B, all of them are below the line of best fit, so again, this wouldn't be a good one. And if we look at D, some are above and some are below, but we see a pattern here. So this pattern shows us that it's not a good fit, which means that C is our good fit here. We have a random amount of points that are going to be above and below our axis, which shows that it's a good fit. So in order for a linear model to be a good fit, right, as it says down here, the residuals on a residual plot must be randomly spread around the horizontal axis. So if we look up here, they're randomly spread around it above and below. So now going into the practice problems. So starting with the first one, it's not too bad. First one says, the table below shows the relationship between the high and low temperatures during 1 week. So we have high temperatures and low temperatures. Which graph represents a correct scatter plot for the data? So first thing to notice is all of our graphs have our high temperatures on our x-axis and the lows on the y. So over here we have our x and our y. So what we want to do is see which one of these has these points plotted on it. So starting with the first point, 57 and 52. So if I go over to 57 and then up to 52, I do not see a point there, not choice A. Now if we try B. B, I go over to 57, up to about 52, see a point. This looks like it's going to be a good one here. Maybe I'll check another point. 6134. So I'll go over to 61, up to 34, see another point. Choice B is our answer here. If we look at C and D, the one thing they did is connect the points. In a scatter plot, we never connect the points, right? Sometimes we'll draw a line of best fit, but it doesn't necessarily have to go through any of the points to be the line of best fit. Now let's take a look at question 2. Question 2 says, a scatter plot with a line of best fit is shown on the coordinate plane below. What is the equation of this line of best fit? So when we're trying to find the equation of this line, remember the two things we have to do is first find the slope and then find the y-intercept. Well, to find the y-intercept of this, this line, I can just look on the y-axis. Right away, I see the y-intercept is 15. So right away, I can eliminate choices A and choice C because those both have y-intercepts that are 5. And this line does not cross the y-axis down here. So now if I want to find our slope, so m is equal to y2 minus y1 over x2 minus x1, we're going to find 2 points here. So this point is right on the line, which is at 8.25. And then also we have a point here at 16 and 35. So we have our x and y. So now we'll plug it into our slope formula. So m equals y2, which is 35, minus y1, which is 25, over x2, 16, minus 8. We simplify this down. 35 minus 25 is 10. 16 minus 8 is 8. And then if we were to simplify this fraction, we'd see that if we divide both the numerator and the denominator by 2, we'll get 5 over 4. So our slope is 5 over 4, which is the same as choice D. So that means that as we go over 4, we're going to go up 5 every single time. And gets rid of B because our slope is not 1/2. All right. Moving on, question 3. So again, as you can see, so far we haven't had to use our calculator for these ones. We weren't given sets of data, so it's a lot of just working with what we have. But we will be using our calculator in videos in the future. So it says here that a group of hikers carried backpacks on a hike. The scatter plot below shows the relationship between the number of miles each hiker traveled and the weight in pounds of the backpack he or she carried. So first thing looking at this is we want to see, we've got miles hiked, so as you go more miles, and the weight of the backpack in pounds. Do we see any sort of trend in this data, right? Are these dots going in a similar either positive line or negative line? When I look here, it seems like a bunch of really random dots. So when I'm thinking about this scatter plot, I'm not really seeing a connection between the miles hiked and the weight of the backpack. So we want to find one of these that talks about how it doesn't really show a clear relationship. So if we look at A, says the longer the hiker travels, the lighter his backpack gets. Well, that's not really true because some people who traveled pretty far had pretty heavy backpacks. The longer a hiker travels, the heavier his backpack gets. Again, we don't see a clear correlation between as the miles hiked increase, the weight of the backpack. C, none of the hikers carried the same objects in his or her backpack. Well, here they don't tell us anything about what they're carrying. So D, there is no clear relationship between the miles traveled and the weight of the backpacks is our correct answer. There's no clear relationship as we're looking, so that's where we have to end there. All right, take a look at the next question, question 4. So question 4 says, Alicia graphed the approximate line of best fit on the scatter plot below, then she made the residual plot shown for the data. So if we take a look at this line of best fit, first thing to notice is all of the dots are either on or below the line. So it's probably not a great line of best fit because remember we want to have a few dots above or a few dots below. And if we look at the residual plot also shows that all of the points were either on the line of best fit or below it. So if we take a look here, we see like this point here is on our residual plot right here. It was 2 points below the line of best fit, so that is below it there. Again, for a residual plot, we want a few above and a few below, kind of scattered randomly, so it doesn't look like a great line of best fit. So if we're looking at the statements here, we want to find which statement says that. Statement A says, the line is accurate because almost half of the residuals lie on the x-axis. Not true because we want some below, some above, or all of them on it, but when we're modeling real life situations, we're not going to see that. So we want a random assortment above and below. B, the line is not very accurate because less than half of the residuals lie on the x-axis. Again, not so much that they lie on it, it's that we don't see any above or below, we just see them all below. C, the line is accurate because all of the residuals are on or below the x-axis. No, it would be accurate if they were scattered. Then D, the line is not very accurate because all of the residuals are on or below the axis. And that one here is going to be correct. Right? It's not very accurate because all of them are on it or below it. So again, we want a scattered assortment above and below. All right, so now moving on to question 5. Question 5, we're taking a look here at a line, and we need to find what is the line of best fit here. So it says the scatter plot below shows the relationship between the weight in tons of an SUV and the SUV's average fuel efficiency in miles per gallon. So if we're given here, we've got tons and miles per gallon. Which equation models the line of best fit? Well, first thing first, so I look at these equations, I can see that it is a line that has a negative relationship here. So it's a negative correlation, which means it has a negative slope. So right away, I can cross off choices A and C because they both have positive slopes, which would indicate the line would be going up as we go from left to right. Then if I take a look at B and D, I could go through and find the slope of this line by picking 2 points, maybe this point here and that point there, and seeing what our slope is. However, when I look at this, another hint I see is our y-intercepts. This one has a y-intercept of 2.7, and our second one has a y-intercept of 23. If we were to extend where this line would go, we would think that it would hit somewhere up here. Well, 2.7 is going to be all the way down here, while 23 is about up here. So I can eliminate choice B because this is not crossing the y-axis at 2.7, which leaves me with choice D. Taking a look at question 6. Question 6 says the table below shows the relationship between the prices of frozen yogurt and the number of cups of yogurt sold that day. Create a scatter plot that best models that data. Be sure to label each axis with an appropriate label. All right, so if we're labeling here, can start. We have, if we're looking up here, we have our price, which is going to be our X, cups sold, Y. So when we're looking at our axis here, right, we'll have the price, and we can put in dollars, and then on the y-axis, cups sold. Now, when we're trying to find what's count by here, we want to see, well, if we look at cups sold, we're going up to about 350, so we wanted to do some sort of counting up to 350, and then when we're looking at the prices only go up to $4, so I think we can count a little bit easier down on the bottom here. So starting with 0, I'm going to count by 50s in cups sold, so every other one will be 100. So we have 100, 200, 300, 400. And then if we're going price, we'll say every other box will be $1. So 1, 2, 3, 4. So it should look something like this, right? So we have cups sold, 0 to 400, the price, 0 to $4. So now if we're putting in this data here, let's zoom out a little bit here. Our first point is 1.25 and 350. So I go over 1.25 up to 350 and put a point. The next one, 150 up to 250, put a point, check. $2 up to 300, check. 250 up to 225, check. 3 up to 175, 350 at 175, and then 4 at $1. So this here is my scatter plot. Then if I wanted to go through and draw a line of best fit, right here we're just modeling this line to the best of our abilities. And my best of my abilities currently do not include a ruler. So hopefully you have a ruler, or you can find something. I'm using these post-it notes as a straight edge. If I want to draw a line of best fit, I want to draw a line that goes through these data points, with some of them being below, some of them being above. Probably could have drawn it a little bit more so that it was a little bit closer to this one here, because we do have 1, 2, 3 below and 1 above. But if it says to draw an approximate line of best fit, that's what we're going to do. If it said to write an equation, right, then we would want to use our calculator. But for this problem, it's not asking us to do that. So this is our scatter plot with a line of best fit. Now the last question here, question 7, has to do with taking a look at residuals. So here, if we want to calculate the residuals, what we need to do is first find the different points that we have here. So we want to create a little table. So here we're going to have our x's and then our actual y's. So actual y. So if we take a look here, if I have a table, we've got 1, 2, 3, 4, 5, 6, 7, 8, 9 points. So we want to have 9 points here. So that's 2, 3, 4, 5, 6, 7, 8, 9. I think we should be good here. So we want to have the actual y's. Then we're going to have underneath it the predicted y's. So predicted, which is when we look at the line of best fit. And then here the residual, which is the difference. So again, extending my lines. All right. So take a look at our first point here. So this point, let's put a little dot on it here. That point, the x value is 2. The y value is 8. But then the y value at 2 here on the line is 7. So when we take a look there, the residual is 8 minus 7, which is 1. Now we do the next point here. So now if we look, the next x value again is 3. So that's this point here, which is, if we go over, right, it's 3 up 8. If we look at 3, it intersects this line of best fit at 6.5. So if we want to find the residual, we do 8 minus 6.5 is 1.5. Then we keep going. So now we have 2 points. So we have this 4 and 5. So I'm going to put 4 with the actual y being 5. And then also 4 with the actual y being 7. Here on the line of best fit, the 4 is actually at 6. So when we do 5 minus 6, this is our first negative residual, negative 1. 7 minus 6 is positive 1. We keep going. Now we see 2 points again, this time at 6. So x is equal to 6, so we'll see that twice. The first one is 6, 4, and the second one is 6, 7. If we look on this line of best fit, when x is equal to 6, y is actually 5. So this is going to give us two different numbers here. 4 minus 5 is negative 1. 7 minus 5 is 2. Then our next one here has an x value of 7 and a y value of 3. So 7 and 3. But the line of best fit actually hits at about 4.5. So 3 minus 4.5 is negative 1.5. So notice all of the ones below the line give us negative residuals, while the ones above the line of best fit give us positive residuals. And then our last two is at the x value of 8 and 8. And the first one, let's say, is 8 and 2. The second one, 8 and 4. At 8, it intersects our line of best fit at 4. So 2 minus 4 is negative 2. 4 minus 4 is 0. So now we've calculated our residuals. So now this is where it gets a little bit tricky, but we've already done all the hard work. So now we have our residuals, and then we also have the x coordinates that they go with. So if we're creating our residual plot here, what we want to do is just kind of make a straight line for our axis. So that can be our x-axis, and then we can have a y that goes up here. On the x-axis, we want to have from 0 all the way up to 8, which was our last point. So here we have 8, and then we'll break this down and say half will be 4, then 6, and 2. And we can have 1, 3, 5, and 7. And then the residuals will go on our y-axis. So if we look at our y-axis, the residuals go from -2 up to +1.5. So we'll say this is -2, -1, 1, and 2. So now what we do is we go through and we plot each of these residuals on this graph here. So the first one, the x value is 2, and the residual is 1. So at 2, 1, we put a point. The next one, the x value is 3, the residual is 1.5. So 3, then 1.5, put a point. The next one is 4, -1. So I go over to 4, down to -1, put a point. And then we keep going through here. So the next one is 4, +1. So 4, +1, put a point. At 6, we go over to 6. Then we're going down, -1, with a point. Then at 6 again, we go 6, up, +2. 7, down, -1.5. And then at 8, we have a -2 and a 0. So this is our residual plot here. If we look here, we see that there is a good amount of scatter here above and below the line. So this line does look like it would be a line of best fit. So this is your residual plot, right? And this is the table that we'd use to get it. Again, with everything else, if you have questions, make sure to reach out. And other than that, good luck, keep working hard, and we'll see you with lesson 5.